Welcome, everybody, to the Satellite Book Club Seminar Series. This is number 229. My name is Dan Lindsay from NOAA NESDIS. The title of today's presentation is Enhancements to Automated Frontal Boundary Predictions with Geostationary Satellite Imagery and High-Resolution NWP Models. Our presenter is Andrew Justin from University of Oklahoma, and our facilitator is Carl Jones, who is the meteorologist and satellite focal point from the WFO Grand Forks. A reminder to everybody that this session is being recorded per the OCIO Privacy Act guidelines. Please keep your microphone muted and webcam off throughout the session. See the pinned message in the chat for more information. We're going to have a Q&A session after the presentation. I'd like to encourage attendees to post their questions in the chat room, and they'll be fielded that way. If you're logged in under an alias, please sign in with your full name or specify your full name when asking a question in the chat. We're always looking for future presenters, so please contact the Tower S team if you're interested in presenting. Emily is putting a presenter facilitator form in the chat. If you, this is how you can indicate that you want to present in the future. And lastly, the training team can help create training materials that may be unavailable. Please contact Ross Van Til for more information or questions on that. Thank you to OCLO, the GEO and LEO programs, and to our facilitator today, Carl Jones. So Andrew Justin is a meteorologist with deep passions for severe weather and AI modeling. His research has been focused on developing machine learning models for automated frontal boundary predictions with the goal of reducing the burden placed on meteorologists of manual analysis of frontal boundaries. Andrew has achieved great success in this research, operationalizing a machine learning model that ingests real-time NWP data to generate frontal boundary predictions at WPC and the Weather Company. Andrew helps to apply this research to figuring out how different types of frontal boundaries influence severe weather hazards and the frequencies with which they occur. Andrew, welcome to Satellite Book Club. Take it away.
Cool. Thank you for the introduction. So yeah, today I'm going to be discussing some improvements I made to my research of developing a model for automated frontal boundary predictions. So I'll be going into a little brief motivation and history behind it, and then discussing the enhancements that we're trying to make with geostationary satellite imagery and the high-resolution NWP models. So the main overarching motivation behind this project is that fronts are associated with many high-impact weather events. You know, they drive a lot of severe weather, and fronts play a crucial role in many, in our daily lives. Frontal analysis is still largely a manual process that is performed by professional meteorologists. So people at the WPC and other NOAA offices still largely do frontal analysis by hand. And meteorologists at NOAA, they draw fronts over North America and much of the Northern Hemisphere several times per day, which is the Unified Service Analysis domain. And so the goal here is, can we develop an automated approach that streamlines and reduces subjectivity in the frontal analysis process? And the reducing subjectivity is kind of a key point here. Back in the early 90s, there was a meteorological workshop described here by Uccellini et al. 92 with the figure on the right. And meteorologists were asked to draw fronts with a specific service analysis or surface map. And you can see that these thick black lines, these thicker black lines are fronts and troughs, and generally there's good agreement near low pressure centers, but then as you sort of branch away from the low pressure centers, the fronts sort of go in all directions, and there's not a whole lot of agreement between that. So the goal here is to reduce that subjectivity and possibly make these analyses a little bit more consistent. So a little bit of background. So back in part of my master's work, we developed FrontFinder AI, which is a machine learning model that is based on the UNet 3+ model architecture. And in the next slide, I'll be getting into exactly what that is. But it locates cold, warm, stationary, and occluded fronts and dry lines. So it doesn't just output whether there's a front or not. It actually is able to classify specific types of fronts and discern between the various types of fronts. So it was trained on 12 years of ERA5 reanalysis data over CONUS using 10 variables given here on the right, and some of them were derived as given in the boldface text. And so what we found is that the model locates and correctly classifies around 3/4 of what we're calling the ground truth fronts drawn by NOAA. So when the model is trained, it is trained on WPC's fronts. So using those as the ground truth, the model correctly classifies around 3/4 of all fronts drawn by NOAA, and cold fronts and dry lines perform better than the other front types. And then in the summer of 2023, I did an internship at the weather company, and FrontFinder was put into operations at the weather company. And then also we made this operational at NOAA's Weather Prediction Center with generally positive feedback from meteorologists. There are some issues in the Southern Hemisphere, as we found out at the weather company, and we've been working to improve on those as well. So the Unit 3+ model architecture, you don't need to know the super deep ins and outs of how this works. But generally, the idea is we input a 3D image with dimensions of latitude and longitude, and then 5 different pressure levels with those 10 variables that I was showing on the last slide. And we perform convolution operations to extract features from those images. So we extract some features from the input image, and then we shrink the image size down through a process called max pooling. And again, the ins and outs of that aren't too important. But when we pull more features from these smaller images, now we are capturing more fine scale details from those images and features. And we repeat that process several times, and then eventually make the image size larger and get it back up to the original size. And what you get at the end here is an output of the probability of a cold, warm, stationary, occluded front, and dry line at each point. So the good thing about FrontFinder being trained on ERA5 data is that you can pass in NWP data from the GFS or ECMWF to produce a forecast of, say, global front predictions up to 2 weeks in the future here. So what you see here are actual predictions from FrontFinder. This is the probability of a front within 100 kilometers, within 50 kilometers of a given point. And I'll let this animate here. So the good thing is, particularly at the weather company, is that they draw fronts up to 120 hours out into the future. And so you can throw in GFS or ECMWF or anything else that's on a 1/4 degree grid, and it will output the probability of fronts at each location. And this version of FrontFinder that you see here is a newer version that I made, and I made some changes to the way I throw data into the model so that it works better in the Southern Hemisphere. But you can see generally you're seeing some of the classic cyclone structures with the cold, warm, and occluded fronts. And then also you can see the dry line showing up in the Southern Plains as well. So overall, it works fairly well, and we've gotten very positive feedback from meteorologists. So while the model works good, there are some downfalls and areas for improvement on this. So the first one is that FrontFinder does not ingest satellite data, and satellite data is one of the sources that WPC and OPC meteorologists reference when performing frontal analysis. In particular, with a lot of cyclones, you can really see like cold fronts and occluded fronts extremely well, and also you might be able to see a dry line with cumulus firing on the moist side of the dry line. And the model does not ingest this currently, so that is one of the areas that we think we could improve upon. And also, FrontFinder cannot explicitly classify baroclinic troughs, which constitute a really large fraction of the boundaries drawn by both WPC meteorologists and meteorologists at the weather company. So on this figure here on the right, I have a surface analysis from this past February, and you can see that just in this small section of the analysis, there are 8 different baroclinic troughs drawn by the WPC. Now, sometimes the model can find these, but they will misclassify them as, like a weak cold front or something like that. But the model cannot explicitly output, this is the probability of a baroclinic trough at this location. And complex systems of fronts often occur with numerous fronts being in close proximity to one another. So you can see several of these troughs, are intersecting, are really close together. And then in this low pressure center down here in southeastern Colorado, you have a stationary front, warm front, and then 2 troughs emanating from that center as well. And so with a resolution like the ERA5 data being on a 1/4 degree grid, we may not be able to capture some of these complex patterns where fronts are in close proximity to one another. So perhaps we need to go into something a little bit more high resolution, which I'll be covering in the latter half of this presentation. So with these aforementioned pitfalls, we've proposed the following research questions. And spoiler alert, we're not really going to fully answer any of these, but these are sort of the things that we're currently investigating. So the first one is, can we achieve greater model performance by introducing satellite data into the workflow? And if we can, is the performance improvement significant enough to justify the burden of retrieving and processing the satellite data? So currently with FrontFinder, you can just call the GFS S3 bucket or whatever, and that's just one data source. You pull it in, you do a little bit of pre-processing, which doesn't take long at all, and then you can throw it into the model and get your predictions. So if we introduce satellite data into the model, is the burden of having to retrieve another data source and process that new data source, is that justified by the performance improvement that we get from the model? And can we also exceed the performance of FrontFinder by training on a high-resolution NWP model, such as the HER or the NAM or other NWP models with higher resolution? And does the high-resolution NWP data allow models to accurately resolve fronts and troughs in close proximity to one another? So, starting with satellite data. So the first thing we did when we started introducing satellite data is our first experiment was grabbing the merged infrared data set from the NCEP and the Climate Prediction Center. And this data set contains merged infrared brightness temperature bands from multiple satellites merged together. So you're looking around the 11 micron level. It's on a 4-kilometer grid, which we downscaled to match the ERA5 resolution. And so this is an example here on the right of that merged temperature from the merged brightness temperature from the merged IR data set. And so the first experiment we did, which was covered in my actually in my AMS poster, was we trained 10 models with infrared data and 10 models without the infrared data over the CONUS using the same time steps in architecture as FrontFinder. So the same timestamps that we use to train FrontFinder, we applied those here as well, doing 10 models with the infrared data, and 10 models without the infrared data. So the initial results were rather kind of actually disappointing. I was expecting a big performance gain, but the results suggest that infrared imagery alone does not add much performance gain, if any at all, to the model. And so on the right here, and of course we only have 10 models of each, so perhaps a larger sample size will reveal something that actually is a better improvement. But you can see that the false alarm rate on the x-axis here and the probability of detection on the y-axis here, the means and the 95% confidence intervals are kind of just sitting on top of each other, and there's really not a whole lot of difference between the two. And training more models on this workflow might reveal a greater distinctions in performance. So again, our sample size here is 10, but these things also take 18 plus hours to train. So it's not necessarily feasible to just keep on training a bunch of these models, especially if we're not seeing a huge performance gain right away. And we also might just need to rework the model architecture to realize greater performance. So that might be adding more filters in the model that can capture more features and draw more correlations between the infrared data and the ERA5 reanalysis. So while they did not appear to show any statistically significant performance gains, the models trained on satellite imagery do appear to be better at resolving wrapped occluded fronts. And I'll have an example here. So this was a winter cyclone that happened in around Christmas of 2023. It produced a big snowstorm in the upper Midwest. And the model without satellite, the models without satellite is shown here on the left, and one of the models with satellite is shown here on the right. So this thick purple line here is the ground truth WPC front transformed to the ERA5 grid, and then contours are the probability of an occluded front within, I believe this was 100 kilometers. But you can see that the model with satellite on the right, it shows higher occluded front probabilities, and it also resolves more of the occluded front as well. So while it doesn't appear statistically that there's a huge performance gain, we do see that with wrapped occluded fronts, there might be some performance gain that can be achieved if we rework the model architecture. And so since that approach really didn't show anything too interesting, we decided to go to raw GOES imagery to the model. So the benefit here, obviously, GOES satellites have several bands that can be used to retrieve different features associated with fronts. And our initial focus was looking at 5 bands to use in future models. So band 2, which is your visible band, and this has interesting implications because if we're training on every 3 hours, then half of the time steps are going to be essentially blank because it's nighttime. Bands 8 through 10, which are your mid, upper, and lower level water vapor imagery bands, and then also we still have the base infrared bands in there as well. And the good thing is that GOES can be pulled in near real time to use in an operational model. But as I was discussing before, does the performance gain get retrieved from the GOES data actually justify the processing time needed to grab all this extra GOES data and process it and then throw it into the model? So the GOES 17 archive only goes back to somewhere in 2018. So our training data set is quite limited, only about 3.5 years for training. We only have ER5 data available to out to 2022 on our supercomputer right now. I'm working on getting newer data so that we can expand the data set. But this raises the possibility of seeing overfitting in the model. So one of the reasons why we went to the merged infrared data set at first is that we had a much larger data set. That data set goes back to the 90s, even though we're not going back to the 90s. But we can create a much larger data set with the merged infrared data, so it would be less susceptible to overfitting. And all overfitting means is that the model, if it has a too small of a training data set, the model will start to learn features in the training data that don't really generalize well. So it'll start learning things like noise. And then when you try to make a prediction on new data, for instance, it will not really generalize the new data as well. And also because we have 5 new variables, which are the GOES bands not laid out on pressure levels, our new models only work in the 2D space. So as I was showing the UNet 3+ architecture earlier, FrontFinder uses 3D images and 3D convolution operations in the model. So we don't have pressure level data for the GOES bands, obviously. And so there's really no logical way to stack the data on top of itself. So we changed the model, these newer models, so that they only work in the 2D space. And the downside of this is that vertical features cannot explicitly be learned by these models, which is unlike FrontFinder. So the model will have to sort of imply how to draw those connections, whereas with FrontFinder, the actual convolution operations are in 3 dimensions, so it can explicitly learn those vertical features. And so some of the initial results here, FrontFinder appears to perform better than an identical architecture trained on 2D features, which we're going to call FrontFinder 2D here. So, I mean, that's not that surprising given that the model can't explicitly learn 3D features. You would probably expect to see a little bit of a performance drop. And we found that adding the GOES satellite imagery also did not have any significant impact on model performance. So here on the right, we have the 5 front types that we're using in the workflow, performance metrics being calculated using a 100-kilometer neighborhood. So any front that is within 100 kilometers of a model prediction, we classify that model prediction as a hit. But there are 7 bars on each of these fronts. So the left one is the original FrontFinder model that is currently published. And then this 2D version of FrontFinder we have here with this double hatched bar. And then I have 5 examples of 2D GOES models on these 5 bars here on the right. And you can see there's really not any difference at all between the models. The only real difference is that the cold fronts appear to do a little bit better with the original FrontFinder, but the 2D models really do not show any difference in improvement, which suggests that perhaps either our approach is wrong or we might need to rework the model architecture. But again, this was a little bit disappointing because I was expecting to see a much larger performance improvement. So some operational considerations. So like I said, FrontFinder can ingest real-time model data to predict frontal boundary positions. So we're going through this workflow here. Let's say we have a GFS forecast hour of 144. If you want to know, hey, what could the fronts look like 7 days out? you can go ahead and just grab the forecast hour 144 GFS, throw it into the model, and then you get an output that looks like that. So if we develop a model that is trained on both GOES imagery and ERA5 data, what we would have here is two data sources. So you would have the forecast hour 144 GFS, and then I'll get into this here in a second, but theoretically you would have GOES satellite imagery. You would pass that into a 2D FrontFinder model and then get the outputs. But the problem here is, how do we get a 144-hour forecast of GOES satellite imagery for all bands of interest? So this goes back to something I was discussing previously, whereas a meteorologist at the weather company, they like to draw fronts, up to 5 days out. And if we have GOES satellite imagery as the predictors in the model, well, how do we get those predictors if the forecast is 7 days into the future? So a presentation I saw at AMS actually gave me this idea. So Randy Chase, who was over at CIRA, I believe he's at tomorrow.io now, he trained machine learning models to predict GOES IR imagery in 10-minute intervals. So over here on the right, basically what he did is he gave the model the satellite imagery from 20 minutes prior and the satellite imagery from 10 minutes prior, and asked the model to predict what the satellite imagery would look like at the current time. So the only two predictors into this model are the satellite imagery 20 minutes and 10 minutes before the actual initialization time. So training a data-driven model to predict GOES imagery on multiple bands could provide a future GOES imagery for our models. So, for example, we could do the satellite imagery 6 hours before and the satellite imagery 3 hours before current time, and see what the satellite imagery would look like at the current time. Now, you can see this kind of does break down. He was using a diffusion approach. The diffusion model tends to just artificially warm everything that isn't convection after about 3 hours, so it kind of breaks down after a while. But this is a possible path, even though I think the workload on this would be kind of insane. But this is a possible route we could take to, again, get that additional data source if we want to predict something like fronts 7 days out with GOES data. And so this gets into the next portion of this presentation, which is we're developing high-resolution front models on the HER. So we started experimenting with training the same UNIT 3+ model architecture on the HER model, which is laid out on a 3-kilometer grid over CONUS, so it's a much more fine resolution than the ERA5 data. And in theory, high-resolution predictions using the HER should produce a heck of a lot more detail with front positions compared to a model trained on ERA5 reanalysis. Now, there are some trade-offs with this. There are, in our domain that we are training on, there are 50 times as many grid points on the HER compared to our training domain with ERA5. So the data set sizes get very large and very fast. So also we have to worry about things like convective feedbacks in the HER, which can contaminate model predictions. And if you're looking at longer forecast periods, you might have some of those convective feedbacks and errors propagate downstream in the model. And that might decrease the reliability when you're, if you looking like 48 hours out on the HER. And so our initial experiments were models trained on dry lines. We found that these things are relatively easier to detect using even really small model architectures. So our first initial experiment was just to train the model on dry lines and see how it did. So in this example here on the right, I believe this is from May 23rd of 2019. These are the probability of fronts within 100 kilometers of each point. So these gold contours here are dry lines, and then blue is cold, green is stationary, and then the red is warm. So the dry line model that was trained on the HER, you can see it produces a much more narrow corridor of front predictions around the ground truth WPC dry line, which is shown here in the solid orange line. So this is something that we would like to see with all the front types. So it's not highlighting, a 200-kilometer wide region of where the dry line might be located. We would like to see something like the HER dry line model is showing. So after we found a model architecture that worked well with dry lines, we decided to try and apply this to all 5 front types. So a model is trained on the HER output They have much more localized front positions, but performance as of right now is generally worse compared to FrontFinder. So all of the ground truth fronts from WPC for this particular day are shown here on the left with the FrontFinder model predictions. And then you can see the FrontFinder HER, it does pretty well generally, highlighting the areas where fronts are located. But you can see that the probabilities are really low and they're kind of all scattered and not too organized, especially as you get near the low up here. So it is promising, but as of right now, we have some work to do. And this might just be something with how we pass the data into the model, and also the fact that there's so many grid points. We have to figure out how to efficiently get the high resolution images into the model without, running out of memory on the GPUs that we're training on. And so some conclusions here. As of right now, satellite data does not appear to have much impact on our architecture's ability to predict front locations. We may have to rework the architecture in order to realize better performance gains. And operational use in this case with a model trained on satellite would likely be limited to current time due to an absence of future satellite information. So if we were to do something like infrared imagery, you could, I guess, theoretically find a way to get something like the simulated IR imagery from like the GFS or something to do that. But as of right now, it appears that this would likely just be limited to current time. And high resolution model data appears to be useful in generating more localized front predictions, which will help us achieve our goal of resolving complex systems of fronts. And so some future work that we're going to be doing here, I addressed this issue at the beginning, but we don't have Barrett Clinic troughs in the model workflow at the moment, and we are planning on including those in a future version of the model, possibly adding outflow boundaries as well. I think this one might be a bit of a stretch, again, given like the convective feedback issues, but that is also another possibility. And we're working to collaborate with meteorologists to develop a model that predicts the locations of tropical waves in the Atlantic Ocean. So this would have implications and utility in something like hurricane forecasting. And then also, we want to conduct an 80+ year climatology of global fronts with FrontFinder or some newer version of the model that does better across the entire EI5 reanalysis record. I think it would be really cool if we could get a global climatology of 80+ years around the entire globe. I think that would be extremely useful. And then we also want to assess the skill of front placement by NWP models like the GFS and HER using ML-derived frontal boundary predictions. So an example of this would be like, how skillful is the GFS at cold front placement 120 hours out, and basically looking in some interval, say every 12 hours out into the future, to see where the model starts to, sort of break down in terms of skill and where we don't get any real utility from the model. And that will do it. So I am glad to take any of your questions that you may have.
Awesome. Thank you very much, Andrew, for that excellent presentation. It did spur up some conversation, which we'll actually get to those questions and comments that was in the chat here in a little bit. But before we move on to the discussion portion of the presentation that I would encourage you to stay for, we'll look ahead at the next Satellite Book Club presentation. So a week from today, on Thursday, April 3rd, noon Eastern, Elizabeth Klein from GOES-R Program Office will discuss the GOES-19 transition to operations. And so yeah, if you have any feedback on this session or the Satellite Book Club, you can use the survey link that will be shared in the Google Meet in-call chat room shortly. You could also contact the Towers S team, Kashad Bowman and Emily Maddox, for questions about the Satellite Book Club or for configuration of satellite products as well. If you have any questions or comments for the presenter, please type them into the Google Meet in-call chat room, as you have been doing thus far. But unfortunately, we won't have the ability to ask verbally. So if you just type your question into the chat, we can ask that on your behalf. We are particularly interested in questions from weather forecast offices and regional headquarters offices. So yeah, well, with that, we'll go ahead and get into the discussion, starting off with these questions. We will start with, and you might have alluded to some of the things that Dan Lindsay was talking about. There was a comment that he had said he believes that one of the post-processed GFS outputs is simulated IR satellite imagery is pretty coarse, but may fit your needs. It sounded like you did kind of allude to that in the conclusion section.
Yep.
And then he also had a question asking if the goal was to find only surface fronts and not, I'm assuming, elevated fronts or in a more 3D type of aspect.
Yeah, so right now the only goal is to find surface fronts because that's what the forecasters draw. So right now it is limited to surface fronts. I think it would be cool to get something that predicts fronts at the like at the upper levels. The problem is we don't really have labels for that stuff. So I'm not aware of any archives that have like, you know, fronts at 700 millibars or things like that. So getting something to training a model to do that, I think would be kind of difficult, but I would think that would be really cool to actually see 3D like front structures output by the model.
Yeah, that would be. I can see now that you explain it how that might be a little difficult, right? And then continuing, Dan talks about surface fronts are only sometimes evident in IR satellite imagery and less so with water vapor bands, since not all fronts are associated with cloud lines, and high clouds sometimes obscure what is happening at the surface. So it's not too surprising that the satellite data isn't helping your model. And I think this is, again, just in reference of kind of only focusing on the long wave infrared channel. And this is, you know, something that popped up in my mind, probably a lot of people on this call right now, that there might be potentially other bands that could might be worthwhile exploring. You know, you said you had mentioned 5 total bands, and I was actually a little surprised to hear that the visible satellite band didn't, you know, increase the skill necessarily. And yeah, I don't know if you had any comments on that.
Yeah, I was kind of surprised too, but I do think like part of the issue is that the fact that, you know, half of the visible time steps are blank because it's, you know, nighttime. But a comment actually somebody made to me a few weeks ago, and I didn't really think of this, but the fact that we're downscaling the GOES imagery and really the IR imagery that we used originally, the fact that we're downscaling it means that we could be losing some more fine scale features in that imagery. So for training something on something like the HER, where we could keep a higher resolution, you know, version of that GOES or IR imagery, I think that might help as well. But I think it's a combination of the fact that, like, especially with visible, half of the time steps are you know, it's nighttime, so it's basically just a bunch of zeros. And the fact that also we're downscaling the data, I think we might be losing some detail by doing that. But
yeah, that is a great point. Yeah, it might be worth looking into trying to preserve that native resolution. Joseph Phillips asked, could AI also be trained on radar data? Thinking if something like this could be useful for identifying smaller scale fronts that are important during severe weather operations, perhaps, you know, filling in the gaps, getting merged data sets to kind of help in the areas where we might be lacking that data.
yeah, absolutely. Yeah, I think, yeah, somebody brought that up actually at AMS, that, you know, training a model on with radar imagery, you might be able to find, you know, more localized predictions for the fronts and things like outflow boundaries as well, which obviously have major implications for things like severe weather events. So I think that's definitely a good idea. But of course we would have to, you know, get another data source and process it and do all that other stuff. So if the performance gain would justify getting all that new radar data, I definitely think that's a doable. Definitely think that's doable.
Awesome to hear that the conversation has already been started. We have Scott Lindstrom. He has asked, could you have sequential models, one that is trained on numerical model only, okay, the FrontFinder, and then as the satellite observations become available, feed model 1, output the FrontFinder into the satellite FrontFinder.
Oh, okay, I see. So train one model only on NWP data, and then as the satellite imagery becomes available, pass the output from the first model into the second model with satellite imagery. Is that the way I'm understanding it?
Yep, I got a thumbs up from Scott.
Okay. I've tried doing something similar to that. I haven't done the sequential approach as you're describing. I have tried passing in like having like two parallel units that are like basically in parallel with each other. So one model, it was a 3D model, grabbing 3D features from the ERA5 data, and then another one grabbing 2D features from the satellite imagery. And that did not work at all. But that's also not a sequential approach. That's more of a parallel approach. So I'm not surprised that it didn't really work. But yeah, I definitely think that's something we could do.
All right. We got all sorts of comments and conversation coming in. We'll try to hopefully get to them all. Let's see. Benjamin Bartos, he was wondering if you have tested any of this in the higher latitudes, such as Alaska.
Yeah, so we do have some of our performance statistics are up there. As in my experience, it does fairly well with things like stationary fronts up there. But as you get into the higher latitudes, obviously you have the issue of with a quarter degree grid, the longitude, grid cells are like right next to each other, and so the gradient and between there, or the gradient of some variable between those two grid pixels is going to be a little bit, iffy for that. So the model does struggle a little bit at higher latitudes, just based on the fact that, the features aren't really as well defined when you're looking at, that fine of a scale. But it does decently well up in Alaska. But there's a lot of room for improvement, especially at the high latitudes. But in my experience, for things like stationary fronts, it does pretty well up there.
Awesome. Glad to hear that we've already explored. Moving on, John Goff asks, do you examine any evidence on predicting locations of the ITCZ? It seemed in your shared animation that there was some evidence of that, maybe in the East Pacific, off West Africa, and possibly showing in the Western Pacific monsoon trough. Just curious.
Yeah, so this is actually an issue that arose before we had FrontFinder. We had a set of 3 different models that were performing that were classifying different types of fronts. So the models didn't know how to discern exactly between the different front types, and that workflow was kind of slow. But in that workflow we had, it was identifying the ITCZ basically as one large stationary front. The problem is we don't have labels in our data that explicitly say ITCZ. So training the model to explicitly identify that would be a bit of a challenge. But yeah, as you said, you can see a little bit of false alarm, quote unquote, because there's no labels down there with FrontFinder predicting the ITCZ. And I think that just has to deal with the fact that you have converging winds and, some convection along it. So it doesn't explicitly identify the ITCZ. It will label it either a cold or stationary front. But we can't explicitly at the moment identify that.
All right, got a thumbs up from John Goff. Zaylong Lee asks, ERA5 is used in the training and trained model is applied to GFS. What could be the potential impact of the quality difference between ERA5 and the GFS on your model?
That is a phenomenal question. And I'm not entirely sure. To be honest, I'm not really sure the exact possible downfalls of that, because in our experience, at least, and I've done a little bit of testing on this, we don't have any skill drop off out to at least 9 hours. So the FrontFinder applied to GFS, there is no drop off in skill out to at least 9 hours. But I'm not entirely sure exactly what the possible downfalls of that would be. Especially if you're looking further out, I guess there could be some issues. Like looking further out, you might have issues with the progression of the fronts and how fast they move. But at least in the short term, there isn't any drop in quality with the predictions. I'm not sure how that looks though further out because we haven't tested that yet. But that's a phenomenal question. I just don't have a clear-cut answer for that right now.
All right, thank you for that question, and appreciate the answer. Probably have time for just a comment and one other question that has come in. Andrew Orson, he has a comment, says, I do think their future is good for greater inclusion of satellite data, and especially on the GeoXO world, where you will have a combination of relatively higher satellite resolution imagery and a couple of extra spectral bands. Yeah, this is actually something that kind of jumped in my mind as well, especially with the inclusion of the 0.91, I think it is, and its ability to see moisture gradients quite well, given the right conditions. But yeah, Andrew also mentioned the hyperspectral sounder instrument, where applicable, can also give a better real-time thermodynamic profile of the entire column, which can aid in surface frontal analysis detail, since you can see where instability gradients are. And then, yeah, the hyperspectral sounder, you might be able to fill in those 3D gaps too, at least on the thermodynamics sense.
Yeah, thanks for the insight there. I'll have to check those sources out. Yeah.
Cool. All right. And last question from Stephen Corfidi. As one who was responsible for doing NMC analysis back in the day, in quotations, that I would have liked to have more time to get things right. How do bad analyses in the training data set affect the FrontFinder's performance? Also, much greater surface data was available to analyzing CONUS frontal positions versus those over the oceans. Would it be possible or advisable to have a separate FrontFinder for data dense versus data sparse areas around the world?
Yeah, that is another great question. Can you repeat the first part of that question to me?
Yeah, sorry about that. We'll go ahead. It's asking, how does the bad analysis affect the training data set for the performance of your model?
Oh, okay. Yeah, so on that end, how does a bad analysis? Well, of course, you will have more ambiguity between your front types. Like actually recently with the huge tornado outbreak that happened about a week and a half ago, as an example, some, like, you could argue that some cold fronts, especially out east, are dry lines. And I've seen some literature on like Mississippi River Valley dry lines, which aren't really drawn that often by WPC. But some of those inconsistencies do result in some discrepancies in the model prediction. So, for example, like last weekend with the tornado outbreak, the large cold front that was analyzed as a cold front, basically all the way from Iowa down to Texas, there was a really high corridor of probabilities for a dry line and a cold front right on top of each other because of the strong moisture gradient across it. And of course, you could argue that that's just a dry cold front. But things like that, it kind of confuses the model, and the model doesn't exactly know which way to go with this. And you really see that with cold and warm fronts, where most cold and warm fronts in the model will have a small stationary front probability underneath it. And so the model is not entirely sure how to interpret the data that you give it. So those are two examples of the potential downfalls from a bad analysis. And then what was the second part was can you train a data dense model and a data sparse model? I think you could. However, especially with FrontFinder right now, since it was trained on only over CONUS and some of Canada, the data availability is pretty dense here in the US. But especially over the oceans, what we found is that it actually has better performance with cold and warm fronts, which to me honestly doesn't really make a whole lot of sense because it wasn't trained over there. So I'm not sure that it would be needed, but it certainly could be done. I don't know if there would be really any extra benefit to training on a data sparse area, especially because if it is data sparse, then you have to question the quality of the training data that you're using. But yeah, since FrontFinder is trained on data dense areas and works well in relatively data sparse regions like the oceans, I don't know if there would be really much performance gain to get from that.
Awesome. Well, really appreciate you answering these questions and providing your insight, Andrew. Thank you so much.
Yeah, absolutely. Thank you for having me.
All right, we'll pass it on to Dan to close us out.
All right. Yeah. Thanks a lot, Andrew. That was excellent. Really appreciate you presenting it at Satellite Book Club today. And thank you, Carl, for excellent facilitation. As previously mentioned, please remember that in a week, Elizabeth Klein from the GOES-R program office in NESDIS will talk to us about the GOES 19 transition to operations, which is planned for late next week. That will do it for today. Thanks, everybody.
Yep. Thank you for having me, guys. Appreciate it.